might have sort of a mix, mix of audience. I'm gonna try to sort of start off like fairly elementary, and I'm aware that there have been talks on quantum mechanics before through this organization, and I believe like the weird behavior that happens in the quantum mechanical level, so in the level of electrons and protons and whatnot, they've already been sort of discussed. So what I hope to add is I hope to essentially give a more mathematical formalism, because there is a side to quantum mechanics that's not often talked about. So there are these weird experiments where electrons behave like particles and waves, where they do all sorts of, weird and wonderful things. But, from a mathematics perspective, the question is, how the heck do we try and come up with a mathematical framework that can give us quantitative results and give us the ability to make predictions as well as possible? And then I hope to talk about what this term, sort of adiabatic transitions, means in this context. Of course, adiabatic is quite a huge word in physics, so I'm sort of specializing here. And then I hope to talk about, then I'll talk about my project and sort of the problem that investigated my supervisor. So I want to start off with classical physics. So, every physics talks pretty much usually has, a picture of Newton, and Newton obviously did very important things. And for us, what's important is that Newton taught us how to mathematically think about classical physics. So this is the physics of sort of the ordinary scale. So for instance, baseball, footballs, rocks, and rockets, and so on. And he came up with these 3 laws of motion. And the second law of motion, F equals ma, allows us to quantitatively predict what objects will do. So if you've ever studied in high school physics, you can, for example, ask a question like, I throw a rock up with a certain initial velocity, what's the trajectory going to be? Where is it going to be 2 seconds from now, 3 seconds from now, and so on and so forth? And this F equals ma allows you to do that. It's known as an equation of motion. Okay. So what I'm going to try and talk through is, through this idea of Hamiltonian mechanics and Lagrangian mechanics, we can get rid of the concept of a force. So F equals ma, this F right here is the force, the net force that is exerted on the body, m is the mass, and a is the resultant acceleration. And essentially, you need this idea of forces, of pushing and pulling in order to make predictions, but we're going to reframe this physics in a very, very nice way. And there are 2 ways to do this. So you can do this from introducing what's called a Lagrangian, which I believe it was talked about in the talk about symmetries. We're going to take a slightly different approach and talk about Hamiltonians. And I'm going to define what a Hamiltonian is in the classical realm and then go into the quantum realm. Okay. So, yeah, I'm gonna try and get technical, but I want to make this as interactive as possible, of course. So, if you've got any questions or comments, please feel free to, interrupt. I want this to be sort of informal. Okay. So I think I will continue. So is everything, can you still hear me and stuff? Is the screen still visible?
Yes, everything is okay.
Okay, great. So, okay, so we want to start with the familiar, and that's classical physics. And we want to develop a mathematical framework for that so that we can take that structure and carry it over to quantum mechanics. So first, I want to define what a classical system is. And all you need to worry about is a system is a collection of n particles. So for example, you might consider the sun, you know, our planet, Mercury, Venus, etc. All the planets that orbit the sun and the sun as well. And that's the solar system. So here's a picture of it, and I couldn't resist to put this old meme. And so, you know, so you can have a system, and the system can be in a state. So a state, sort of loosely speaking, it's a configuration that the system can be in. So imagine we freeze, you know, we freeze at a moment of time. If we look at the location of all of our objects and we know how fast they're going, or more specifically what their momentum is, that is a state of a system. So I'll introduce a more mathematical way, and then I'll pause if there are any questions. So classical physics, a state of a system is a particular configuration of a system at a given time t. So how could I fully describe the state of a system? Well, I just have to give you, so you just have to give me a list of the position of each of the particles, so where they are located in space, and the momentum of each of the particles. And you can think of this as a point in some m-dimensional space. And I'll go to a very, to a concrete example. So I'll pause here if there are any questions. All right, I shall continue then. Okay, so this leads us to the concept of a phase space. So a phase space is the set of all possible states a system could be in. Okay, so here is this very overused example, the simple harmonic oscillator. So physicists have a pretty unhealthy obsession with this system, but it's a rather simple system to study. So what we've got here is a mass, it's on a spring, and the spring would really like to be at this length. As you can imagine, if I pull my mass over here, then it's going to want to go to the left, right? And if I let go, I'm going to get oscillations. And well, we'll ignore air resistance stuff for now. So it will perpetually oscillate forever. So how could we think about this in terms of phase space? Well, what would the state of this system be? So the system right now is just one particle. It's the mass. Right? We can forget about the spring. And we can imagine this mass being on a number line. So you can give the position of the particle. So let's say it's at x is equal to 1, right? Of course, I've also got to know how fast it's going, so what the momentum is. So for example, if I'm holding this guy at rest here, that would correspond to x equals 1 and p is equal to 0. And if I draw on my y-axis the possible momentum this can take and the possible x values this can take, I would be somewhere here. So I hope that you can appreciate that I've encoded the state of this system by a single point. Are there any questions? Okay. So I'll continue. Now let's say I let it go, right? Well, what's going to happen? So I started off, so this was my initial state. Then the particle is going to want to go to the left, right? Because this is all stretched out. So at some moment of time, it will be traveling to the left with some momentum. And that momentum, I can take that to be negative. So this point would move down like that. And then if I wait, what am I going to get? It's actually going to trace out an ellipse. So here, this is all the way stretched out. Here, it's passing through the equilibrium position. Here, it's compressed. Then here, it's passing through the equilibrium position again, going to the right. So how's that? Okay, I'll carry on. Okay, so, all right, so I wanted to discuss what a Hamiltonian is. So a Hamiltonian is just something that takes in, so it takes a particular point in my phase space and it assigns a number to it. So, you know, mathematically speaking, it's a function in the phase space and it outputs a number. So very often this Hamiltonian is just the total energy of the system. So, you know, if you studied physics, I hope this is somewhat, you know, I hope this is familiar. It's just the total energy of the system. Now, you might notice that, okay, so the Hamiltonian is actually a fixed number because the total energy remains constant. And so the orbits would indeed be an ellipse. So if I take this and I set it equal to a constant, I plot x and p, I get an ellipse. Ellipse is just a stretched out circle, okay? All right. Okay, so, right, okay, so I'll continue then.
Sorry, can I ask something?
Yes, please.
I know like ellipse isn't like the same as unit circle, but we use unit circle in mathematics and calculus a lot. I don't know, I was wondering like if there's any link between like unit circle and like this image you just shown us.
Yes, thank you. Yeah, thank you very much. That's a great question. So, okay, so a unit circle, I hope so imagine you're familiar with the equation of the unit circle. It's something like this, right? X squared plus y squared is equal to 1, right? Are you familiar with that? Right, yeah. So essentially, imagine that my P here is my X and, the P here is the Y and X here is this X right here. So I can take this unit circle and I can divide. So, you know, I can take this unit circle equation and divide by, let's say, a number, a squared, and I can divide the y squared by a number, let's say b squared. Okay, can you see what I'm drawing on the screen?
Yes, I see.
So what I've done here, so let's think visually what's happening. I start out with my unit circle. What I've done is I've made my x coordinate go to x divided by a. So this used to be at 1. I've stretched it out. Now it's at a. And I've also stretched my y coordinate out. This used to be at 1. Now it's gone to b. And so when I do that, I get an ellipse. How's that so far? I'm just taking the x and the y and I'm just doing stretching on it. It's a graph transformation.
Okay, thanks.
Yeah. Yeah, and then this is, so this is basically of that form. So an ellipse is a more general equation. It's a more general form of a circle, right? If you take a equals b equals 1, then you get the unit circle back. And if you take a equals b equals r, then you get just a general circle of radius r. So it's centered at the origin. Does that answer your question?
Yes, thank you.
Okay, brilliant. Okay, so I shall continue. Okay, so now I would like to, okay, so go back. Okay, so now I wish to describe what an adiabatic problem is. So you saw the term adiabatic in the title. So what does that mean? So we can actually talk about this in the context of classical physics. So this Hamiltonian, this is the total energy of our system, right? So I hope you appreciate that this does not depend on time in any explicit way. It only depends on P, and it depends on X. So what I do is I make my Hamiltonian depend on time. So this K right here for the spring, this is known as the stiffness. So it's a spring constant, and this describes how stiff my spring is. So imagine, okay, so this is what I've said. So there's no explicit time dependence. Now imagine that I make my stiffness depend on time. So I'm making the stiffness grow gradually, okay? Now the question is, what would happen? So, okay, so Okay, you can think of, so we're talking about this mass on a spring, but you could also equally consider a pendulum as well, which you might be familiar with, right? You've got a mass and it's suspended by some string, and that string has got some length L to it. So I'm going to try and exit here and show an animation, because animation is worth 1,000 words, I guess. So, okay, so this is a similar portrait, a phase portrait as before. So, okay, so if my pendulum is a specific length, then I'm going to get an ellipse being traced out. And if I sort of, you know, okay, this animation does not want to work with me. Basically, if I change the radius of this, if I make the length larger, then the ellipse I'm going to get is going to deform. Okay, the ellipse is going to deform. The adiabatic theory tells us that it'll deform in such a way that the total area, this area enclosed, is constant, it's fixed. Does anyone want me to repeat anything I just said? Okay, so I'll carry on. So so yeah, adiabatic really means, so you've got an adiabatic problem where the Hamiltonian depends on time. I'm sort of deforming the Hamiltonian very, very slowly.
Actually, I wonder something. You said that the area will be the same, but I mean, mathematically it is okay, but can we say that physically the energy of the total energy of the system also remains the same?
So, okay, that's a really great question. So not in this case, because I'm making the Hamiltonian. Remember, Hamiltonian physically means the total energy of the system. So I'm changing it in time. So, you know, physically, in some sense, I have to change the energy of the system. So, you know, you could think of this from a physics perspective, right? If I go back and I'm changing the length of the pendulum, I have to put work into it, right? I've got to lift the, you know, object up or to drop it down. So the energy won't be fixed in time, and that's quite important.
Yes. Mm-hmm.
I have a question. So when you say that the area in the phase space is constant, does that mean that the number of states it can possibly have is constant? It's not changing.
The number of states the number of states in this setting is infinite anyway, that it can have. So in terms of the states sort of, again, you know, given an initial starting position, right, you get an ellipse, and that ellipse simply deforms. So what do you mean exactly by the number?
I want to ask, when you say that the area will remain constant, what exactly physically is remaining constant if the area in the phase space is constant?
So physically speaking, so physically speaking, that turns out to correspond to, roughly speaking, you take the Hamiltonian and you divide by the frequency of oscillations. That is known as an adiabatic invariant. So I can't go too deeply into that, but from a physics perspective, I'll write that down here. So that's known as an adiabatic invariant. When we talk about quantum mechanics, it'll be clearer what physical thing is remaining constant there. But essentially in this problem, you can think of it as you take the Hamiltonian and you divide by the frequency of the oscillations, and that's the thing that remains constant.
Thank you.
Okay, cool. All right. Okay, so guiding question here. So now let's go to quantum physics, right? So you might be aware that things on the very, very tiny scale behave very strangely. So the question is, how can we put this physics into a mathematical framework? Now, if you're approaching this as a mathematician, structure is extremely important. So you want to take sort of the underlying structure of a theory that already exists. So in this case, classical physics. and you want to sort of somehow carry that over. So we talked about a Hamiltonian, and we've talked about, well, we talked about Hamiltonian, we talked about a state of a system. So these ideas, so states, you know, systems and Hamiltonians, they're going to carry over to quantum mechanics, but in a rather different form, because, well, when you talk about quantum physics, a state cannot be a list of momentum and position anymore, because those things don't really make sense at that level. Okay, so I'll continue, yes. So, okay, let's now jump into quantum physics. So suppose we've got a nice, happy little electron, okay? It's actually rather big, but yeah, nice, happy electron. Now, quantum mechanics tells us a couple of interesting things about this electron. Firstly, it can only occupy certain discrete energy levels. So if you have an electron in a hydrogen atom, it can only exist in this energy level, in this energy level, maybe this one as well, you know, and so on and so forth. But it can't be anything in between. It can't have an energy in between any of them. Okay. And okay, now you might be wondering, sort of, from a physics, you know, from a physics perspective, what does this all mean? So this sort of comes from the idea of a particle in a box. So you sort of have to think of electrons as being particles and also sometimes waves as well. And the way that I'd like you to think about an electron, if you've got it in an atom, sort of a very crude model in one dimensions is you might take an electron and you might trap it in a box of length L. So it's one dimension. So the electron, you know, abstractly how it exists is I want you to think of it as a standing wave. Okay. Has everyone met the term standing wave before? Is this familiar? Okay. So, you know, it can either exist like this, so a single node oscillating up and down. It could be two nodes like this, or three or four, and so on and so forth. And each of these, physically, they correspond to different energy levels that an electron can be in. Okay. Yeah, so be careful. So the height of this wave, that's not really, it's not to do with the energy of the electron. The energy is really captured by the fact of how many of these, you know, valleys and troughs and whatnot there are. Okay, so I want to talk about now adiabatic theory. So what's the analogous problem that we've talked about in classical physics in quantum physics? So here, the length of the box is a very important variable, right? It's a very important parameter in my problem. Now, this system has got a Hamiltonian associated with it, and talk about what a Hamiltonian is in quantum mechanics in a bit. But you know, the length of this box is an important variable. And imagine now that I slowly sort of take it and I move it, right? So I make this length dependent on time. Okay, and I change it very, very gradually. Okay. So what's going to happen is, okay, I'll jump over here. I hope you can see my whiteboard. So let's consider the ground energy state, and this is the length L of my box. If I do it very, very gradually, what we find is that the basic shape remains the same, like that. So imagine I'm taking this and I'm very, very slowly and gently pulling it forward. I'm tugging it forward. I'm going to get the same basic shape. So if this was the energy level n equals 1, so the ground state, it's going to remain in the ground state as well. So from a physics perspective, this is rather like, this is rather stark what this is. This is telling you that if you change your Hamiltonian really, really slowly, then typically the electron would want to remain in the same energy level. It's very, very unlikely for it to jump between energy levels. Okay, I'll continue unless I get stopped. So, okay, right. So a second thing that quantum mechanics tells us is that so there is no way for you to know beforehand what energy level you'd find the electron in, okay? So the best you can do is give probabilities. The best you can do is say how likely it would be that if you were to measure the energy level, you'd find it here. How likely is it that if you were to measure the energy of the electron, you'd find it here, and so on and so forth, okay? So it's very, very, very different from everyday life. It's very, very different from everyday experience. The electron will just decide sort of last minute where it wants to kind of show up. And the best you can do is to sort of guess how likely that will be. Going down. Okay, so yeah, so now I want to talk about what a state is. So for quantum mechanics, I can tell you what a state cannot be. It cannot be a list of position and momentum anymore, right? I can't do that anymore. It's not that anymore. Instead, we're going to have to think a little bit. So, okay, so let's just focus on two levels. So let's say that an electron can exist in two levels, okay? So it can be either here when you do a measurement, or it can either pop up here, right? Now, you might be in a situation where it's equally likely that the electron will show up in either energy level, right? So that's one possibility. Or you might be in a situation where the electron is more likely to show up in the bottom energy level, for instance. Or, you know, you could be in a situation where the electron is more likely to pop up in the upper energy level. What have I done here? I've actually described to you different states that my electron can be in, okay? So we've got the system of an electron in two possible energy levels. And, you know, a state is simply, so if I want to describe a state of an electron completely, I have to give the probability of each outcome of an experiment, and that's the best I can do. Okay, so you might ask what the Hamiltonian is going to be. So in quantum mechanics, this idea of a Hamiltonian carries on. I will discuss this more if I get asked later on, but all I'm going to say for now is that a Hamiltonian, typically it's a matrix. So a matrix is just a collection of numbers. So you got a bunch of numbers in sort of an array, right? So 0, 1, 3, so on and so forth. And this Hamiltonian, so from this Hamiltonian, right, once you specify the Hamiltonian, you get the two energy levels from that somehow, right? It gives you what these two energy levels are. And then a particular state would be a way of, telling what the probability is of an outcome. Okay, so I should mention this. So more formally, so a state in quantum mechanics is often given by something called a wave function, right? So, this looks alien to you, that's perfectly fine. The point here is that this guy right here represents the electron being in the lower energy level, right? This represents the electron being in the upper energy level, okay? And so these two are numbers. So these two are numbers that that you are free to adjust. And if this number is much larger than this, then this is corresponding to the case where the electron is more likely to be in the upper energy level. Conversely, if this and if this number is much more larger than this one, then the electron is more likely to show up in the bottom energy level. Okay, so I'm sweeping a lot of mathematics under the carpet, but feel free to ask if you want me to explain that more. Okay. All right, so I think it's time now for me to finally sort of try and state what the problem is. So this is a very classic problem. So it's got a very rich, nice literature. This goes back to the all the way to the 90s. Well, a big breakthrough sort of came in the 90s with someone called Sir Michael Berry. So Sir Michael Berry, and yeah, he published a paper about this problem, and then there were more sort of attempts at this problem. And I'm going to just briefly walk you through what the problem is and a few ways to think about it. So let's say that I have a Hamiltonian, and this Hamiltonian describes an electron being in a two-level system, okay? So it could be two energy levels, or it could be, you know, it could be the experiment if the electron is hard or soft, if that rings any bells from previous talk. Now, okay, so the energy level, right? We're gonna imagine that it depends on time. So suppose that my system has two energy levels, and at each moment of time, it's exactly the same. So my two energy levels do not change at all. My Hamiltonian is not dependent in time, okay? Then what we know is that if you do a measurement and you find that the electron is in one of these energy levels, then it will remain in that energy level forever, okay? So no transitions would happen, and life would be pretty boring because, you know, arguably a lot of chemistry is based on the fact that electrons can transition and give off energy and all sorts of things like that. Okay, so what we do, okay, so let's say I put my electron in the upper energy level and no transitions would occur, okay? And this is sort of to do with the adiabatic theorem before. Now, imagine that I make the energy levels wobble around a little bit, right? So, you know, you got the energy levels like this, and then they move sort of up and down. They oscillate, let's say, okay? But let's say they oscillate very, very gradually. So my Hamiltonian is now dependent on time, okay? So what's going to happen? Well, I've touched on this before. You know, you can think back to the particle in the box and moving the length of the box, you know, changing it very gradually. Sort of what's going to happen is that the electron is going to stay in this energy level, but have a, like, okay, so it's going to most likely stay in this energy level. So it's going to follow this, right? But there's going to be a tiny probability that it will jump down. Okay, there's going to be a tiny probability P that it jumps down. Okay, so that's crucial. Okay, there's a probability P that the electron will jump down. And the question is, what is this probability? Okay, now, if just in case you want to read up more about this, there is actually a rather basic example of this. And this is to do with something called Landau-Zenner transitions. Again, if I've got time later, I might go into that a bit. Okay, so this is a very basic example. For this, you can compute everything explicitly. Now we're going to need some, you know, some variables in our problem. So let's let a positive number epsilon describe how much wobbling happens in the energy levels. So if there's less wobbling, so if there's a lower value of epsilon, then there's going to be, P is going to be lower. The probability that it jumps down will be lower. Okay. So the question is, given a value of epsilon, So if you know how much the wobbling happens, what is the probability that the electron will transition after we have waited for a long time? Okay, I know that I've introduced quite a bit, so I'll just pause here and wait if there are any questions. All right. That's good. Okay.
I have a question, actually. The fluctuation of these energy levels, how do they occur? I mean, do we see it in frequently, or is it something like we apply an external field?
Yeah, we apply an external field, exactly.
Okay.
So you can, one way you can get this is you can turn an electric field on and you can make the electric field oscillate very slowly. That's one way you can do it. This even applies to, if you're familiar with a concept called spin, you can even apply it to that and have a magnetic field. You know, it's very, very, very sort of a general way you can do this experimentally.
Is it the case that actually we are not fluctuating the energy levels, but we are fluctuating the electron, right? Because the energy levels are not physically objects, that they are just the probability, they correspond to probability values.
So the energy levels, so the energy levels are physically significant, right? So the energy levels do physically, exist. And, so of course there's a lot of weirdness with it. Like I have to talk about probabilities and stuff, but, you could imagine that at every moment of time here, I make a measurement, and at every frozen value of time, the energy of my system would be somewhere like this. And there's going to be a probability that once you make the measurement, the electron will appear, upstairs or downstairs, so to speak.
Okay.
But the point is that the energy levels are physically meaningful, right? So think of the if you go back and you think of the hydrogen atom, the energy level diagram for that's perfectly physical, and you can distort the energy levels by applying electric fields and stuff, and that's there's a whole rich field dedicated to that called perturbation theory, and this sort of borrows.
Because of the perturbation.
You perturb the Hamiltonian.
Okay, thank you.
I had a question here as well. It might be a stupid question, but is there a relation to symmetry breaking here? So can we say that there is the system is symmetric in the start, but once there is a perturbation, there is a probability of symmetry breaking and going, there is a probability of transition between these two energy levels?
Oof, right. That's a pretty deep question. So I honestly don't think I could give a proper answer to that, but what we're considering is a rather simple setup. So the symmetry I think you're talking about usually correspond to what's known as degeneracies in the energy level, right? So the symmetry breaking you might be thinking about is, you apply a magnetic field and you get this thing called the Zeeman effect, for instance, and you get splitting of energy levels and so on and so forth. So nothing like this is happening here because we're assuming that the energy levels are non-degenerate. Does that mean anything? Explain anything? So I don't think that there's really any symmetry or anything necessarily happening. I'm taking a very special case. So, if it interests you, so this idea of degeneracies are to do with the Hamiltonian and whether their eigenvalues are simple or not.
Okay, so the symmetry breaking can be discussed when there is degeneracy in the energy levels?
Exactly, yes. So if you've got degeneracy in energy levels, so degeneracy, what does that mean? It means that, it means that there are multiple wave functions that correspond to an energy level. So there are sort of multiple ways to be the same energy level. And if I apply, for instance, a magnetic field, then, so if you think of, so this is all one dimensional, but if I go into higher dimensions, that's when I get degeneracy. So, if I go into like 3 dimensions and I've got a sphere, right? And I treat the hydrogen atom as a sphere, there's a heck of a lot of symmetries there, right? Because it's a sphere. So that would correspond to degeneracies occurring in the energy eigenvalues. But then if I suddenly turn on a magnetic field, I break that symmetry, just kind of like how you're describing. And that would correspond to the energy level splitting. And that's known as Zeeman splitting. And
I understand. Yeah, so basically when they are not degenerate, then there's a, they're together in the same place, but once you apply some external effect, then there's a probability that they can go in either of the degenerate states, and then the symmetry will be broken if it goes to one of the states.
Yeah, and how do you work that out? Perturbation theory, baby.
Right.
Use perturbation theory for that. But yeah, so in this problem, because the problem of figuring out the probability of transitioning is so difficult for even this simple case, we just do not dare to go into that territory. At least I don't dare going into that. Maybe, if you publish something in that, then I'd be more than excited.
Thank you very much.
All right, brilliant. So, okay. So yeah, so this is a very prototypical problem. And it turns out that there's no really satisfactory answer to this. It's very approximate, a lot of the approaches to the problem. So, okay, now I'm gonna kind of show possibly the ugly side or the beautiful side, depending on whether you're, depending on who you are. I just want to quickly mathematically state the problem. So here, okay, essentially, the setup of the problem is that I've got this Hamiltonian and it's got the 2 levels, and I want to make the levels sort of wiggle about, right? And as I said, as I alluded to, a Hamiltonian is a matrix. So it'll turn out to be something like this, right? Where rho and theta are functions, okay? And basically this is known as the Schrodinger equation. So, okay, so we said how in classical physics, you've got the state of a system, and the whole game there is to figure out how the state will evolve. Here, the state is replaced by this idea of a wave function, and you want to figure out how the wave function will evolve in time. And this is the equation that helps you do that. I can go into more detail if asked, but that's sort of the idea. This epsilon right here is how we control how much oscillation happens. So sort of what we do in some sense is that we scale time in a particular way. So yeah, I'll very briefly say this. So basically, whenever you've got an adiabatic problem, the point is that you've got 2 scales, 2 separate, separable scales. So when we had, for example, the silly thing of the pendulum and I was changing the length of that, I said I do it gradually, right? What does gradually mean? It means that I make the length change small, like very slowly compared to the period of oscillations. So, for the pendulum problem, the time scale associated with changing the length is much, much, much larger than the time scale associated with oscillations, okay? So you've got a separation of scales there, and that's where adiabatic theory can really come in. This isn't limited to just time scales, by the way. So if you've heard of something called the Bourne-Oppenheimer approximation, that assumes that the mass of the electron is much, much, much smaller than the mass of the nucleus. Here again, you get 2 very well-defined and very separate scales. And that's all where, adiabatic theory comes in. So here, what are the 2 scales? So what you typically do is you start off with what's known as a macroscopic time scale, and you got an epsilon, which you multiply by that, and that gives you another time scale. And these 2 are 2 separate time scales, and sort of if you incorporate that, you get this. Okay, I can sense that I'm rambling a little bit, so yeah, that's the idea. Okay, so the okay, so the H, so this has got energy eigenvalues and it's plus or minus rho of t, and they're non-degenerate, as I alluded to before. So they each got what's known as an eigenstate associated to it. So, you know, this is, if you're familiar with matrices and all of that, this is an eigenvector. Okay, so this is just the mathematics, and I make epsilon really, really small. I'm assuming that. Okay, continue. Yeah, and so what I think I said this. So how I start off is I put my electron in the upper energy level at t equals minus infinity. So at the beginning of the universe, say. And then at around t equals 0, I make my energy levels wobble around, and then the wobbling dies down. So I capture that by specifying it like this. And yeah, and then it turns out that you can simplify the form of the Hamiltonian and all that. So this is just the technicalities. Okay, so what is known? So a lot of things are known, of course, in the literature. A lot of things are known that I have no clue about. But one thing is that this is something that the adiabatic theory gives you, okay? So suppose that P is the probability that we're after. It would be really nice if I could get a very simple formula in terms of epsilon, but I can't do that. This is real life. This is real life for a mathematician, you know, physicist. So suppose that P is the probability of the electron transitioning. What we know, well, one of the things we know is that you can bound the probability from above. So this first inequality, this means that there is a constant C1 where P is less than or equal to epsilon. So this, by the way, means that it's big O of epsilon, if any of that you're familiar with. So basically there's a number such that this inequality is true as epsilon goes to 0. Okay. It's also true that the probability is less than or equal to some other number times epsilon squared. In fact, the probability is also less than or equal to some other number, epsilon cubed, and so on and so forth for all n. So this is what is known. Okay, I'll pause here if there are any questions.
Actually, can you just repeat what are the time scales?
Yeah, sure. Yeah, I glossed over that. Sorry. So, okay. So, essentially, I didn't go into much detail, but the idea is that this is more of okay. So, how can I do this? Okay. So let's go back to the pendulum, right? So here the time scales were, you had the time scale associated with the length, me changing the length of the pendulum, and you have the time scale associated with the period of oscillations, right? And I say, so what I mean by this being well separated is that, you know, I could write this in some sense as T oscillations is equal to epsilon times T length. So epsilon is always a small number. Okay, so this is where the separation of timescales comes in. So often when you state a problem mathematically and you want to use adiabatic theory, you have to say something like, let T be, you know, the macroscopic time variable and let one of these be the microscopic. Is there anything
This is an
specific?
assumption, right?
This is an assumption, yes. So we're working in the adiabatic limit. So this is only valid for epsilon going to 0. Okay. Okay. All right. That answers your question. So yeah, this is an assumption. Yeah, exactly. Right. So, okay. So what's known is that you can bound this by epsilon to the n. Okay. Now, this might give you the impression that it, you know, this might, just looking at this, it might give you the impression hang on, this probability less than or equal to epsilon to the n for all n, isn't that saying that the probability is basically 0? So it's not. So this is where the difficulty comes in. This is what makes the problem difficult. These constants, I've not told you what they are. In fact, what it turns out that these numbers, if you think of it as a sequence, it tends to infinity. Okay, so this is a really, really badly behaved problem. If you know, often you try and estimate what this probability is by taking an infinite series, so adding them all together, but that infinite series doesn't even converge. So what I'm trying to motivate here is that you need, you need this thing called asymptotic analysis. That's where that theory comes in. And if you look at the papers, what they often do is they try and estimate what P is by truncating this series right here for an appropriate value of n. Stop there and they get an estimate. So are there any questions?
Oh, hey, Sean. I have a question.
Hello. Hello, Jacob.
Hey, nice to see you here.
Nice to see you too. Yeah. Go ahead, mate.
So
embarrass me.
Sorry. So we know that it tends to infinity, but do we know how fast it tends to infinity?
I don't. I mean, you can probably look at the papers. There's probably a lot of information about that. It tends to infinity. Now, actually, you can get a better bound for this. You can say that it's of order epsilon to the, I think it was minus t divided by epsilon. So that might give you a better idea of how quickly that goes to infinity. It goes to infinity fast. So you have no choice but to truncate the series. Otherwise you get an infinity as your answer.
Okay, thank you.
Okay, brilliant.
So
okay.
Are these are these constants C1, C2, and so on? Are they in any way related to the amplitudes that we define in the wave function from the Bourne's rule?
Yes. So the probability, I mean, the probability is the amplitude of the wave function.
Okay.
And yeah.
So it is just the epsilon multiple of.
Yeah.
Okay.
Yeah. So the probability amplitudes are order of epsilon to the n for all n. So yeah, they are related. They're related by an inequality. Okay. All right. So okay. So okay. All right. So I want to just briefly talk about sort of where we took this project. So it turns out that, you know, this idea of a wave function is very, very abstract. So it turns out that instead of thinking of things in terms of a wave function, you can actually just associate a state to a point on the sphere. And actually, if you're wondering, this is in fact something called a Bloch sphere. Okay, I'll just mention that in passing. So let me try and sort of visually describe this. So, okay, so instead of a wave function, okay, it turns out that you can describe the state of a system by a matrix instead. And then this matrix has got certain coordinates to it, and just by doing some math magic, you can reduce the problem to describing, okay, so I'm just gonna skip this. Okay, yeah. So by doing some sort of math magic, you can completely concretely describe the situation where the electron is in the upper level with 100% probability. So if you recall, this is how we described it before. So this is the traditional way of describing it. But it turns out that you can just think of that as a point on the sphere, so the North Pole. Okay. But this has nothing to do with phase space, by the way. This is just a convenient way of thinking about this state. Then, very nicely, if you want to think about the electron being in the lower level, then you can think of this as the South Pole. And so in general, anywhere in between is just a point on the sphere. So remember how one of the states is that it's equally likely to be in either energy level. That would be, as you might expect, just the equator of the sphere. So, okay, I know I'm getting to the end of the time. So if you know the point on the sphere, if you know at every point, if you do this problem, you run this problem, it will start. So because we start at the upper energy level, this is where you begin, okay? And if you can figure out where this point moves, you would know what the probability is of transitioning occurring, okay? So I suddenly jumped topics. I'm aware of that. Are there any questions?
So the points on the sphere are basically dependent on the constant you mentioned before, right?
Yes. So yeah. So psi of t is a1 phi plus a2 phi minus. These are numbers. They're complex numbers, but never mind that. And you can figure out what this is from that. So okay, yeah. There is off the top of my head, I can't see a very direct link. Instead, you reformulate the state here by a matrix. And then the coefficients for this matrix is related to that. Okay. If I've got time at the end, I could go through the details if you wish me to do that. Does that answer your question?
Right, yeah, thank you.
Okay, yes. So, but they are related to these guys. So, right. So what was our problem? So the problem we were studying is that, you start off with the electron happily sitting in the energy level, and then you make it upset. You upset it by wiggling the energy levels around, and then you make it go back to normal. And that would correspond to you starting on the north pole of the sphere, right? And then you would gain a probability amplitude of transitioning down, right? So that's the sort of correct phrase. You gain a probability of going downwards. So that means that you get a little bit of this mixed in to your states. And so you end up straying away from the North Pole, okay? And then, you sort of make some sort of trajectory on this sphere. And the question is now, so I hope, see that we've reduced the problem to figuring out what the trajectory of the of this point on the sphere is, okay? So we started off with wave functions, and now we're just asking, how does this point move on the north sphere, sphere, given given the value of epsilon and all of that, given the parameters. So it turns out, first of all, if you know the point on the sphere, then you know the probability, and it's given by this rather simple formula. It's 1 minus the z coordinate on the sphere divided by 2. So you can think of the probability of it not transitioning as being an average between the point where you're at and the North Pole, the average height between the two. So that's the probability that you don't transition. And then you can just sort of, if you're interested in the probability as t goes to infinity, you just see what this goes to as t goes to infinity. Okay. So now, what's the obvious question? The obvious question is, well, Sean, that's really nice. That looks very pretty and all. But how on earth do I figure out what this z is? So how do I figure out what the x, y, and z coordinates are? Well, I'm glad you asked. I'm glad I asked. It turns out that you can figure out x, y, and z from a set of differential equations. And this is actually not too bad to analyze. Now, just because of time constraints of the project, I just ended up trying to numerically simulate this with MATLAB. If we just take a look at this and try and see through this equation, right? What do we notice? So we notice these epsilons appearing. And if I make epsilon very, very tiny, so if I kind of make it go to 0, I end up getting something like this. Okay. Now, okay, so don't be afraid of getting this wrong. Can anyone sort of hazard a guess as to what this might be describing? So what the solution to this might be? Let's pause here.
Cosine and sine, right?
Brilliant. Yes, it's cosine and sine, right? So this means that x is cosine something. And what would the frequency be related to in this case?
1 over epsilon.
Yes, so, you know, the tinier the epsilon is, the more you're kind of wiggling around. So actually, before doing anything, you can sort of guess that the trajectories will kind of probably be a spirally shape, okay? And then you add this sort of other term to it, and it deforms it just a little bit, okay? So what's kind of nice is that before you even bother to do anything with this, you can guess sort of what it's going to look like. And this z coordinate doesn't even depend on epsilon, interestingly. And so, yeah, plotted this in MATLAB, and guess what? To no one's surprise, it is spirally. So what does this data mean? So I've plotted the trajectories for various values of epsilon. So epsilon is equal to 1 is this, and notice how it's a wider trajectory. Now, what does this mean again? Well, oh, someone gonna suggest something? Okay, so epsilon is equal to 1 is a wider trajectory. So what might this suggest for the probability of transitioning?
It's greater compared to the other smaller.
Yes, it's greater, right? Because the probability of it not transitioning is the average between these two. So it's greater, right? And that's exactly what's expected, right? So if I wiggle this a lot, then it's going to have a much more chance of wanting to jump down. And of course, if I make the epsilon smaller, you get no prizes for guessing that the transition probability will also decrease, which is what's expected. Okay, so you can see that by these getting sort of tighter and tighter, and eventually going back near the North Pole. Okay. Pause here. Right down. Okay, so I hope you appreciate this is, you know, pretty interesting graph probably, and it sort of confirms our intuitions. Now the question is, well, can I see this probability as a function of time? And yes, you can. So I also plotted the transition probability in terms of time. Again, the assumption is that epsilon is small. Notice how tiny the probabilities actually are. So that confirms the idea of the adiabatic theory. And notice how the transition jumps at around time t is equal to 0, because we shake the system at around t equals 0. By the way, this is known as the scattering regime. So whenever you are taking your system and you let it be whatever it wants to be, and then you shake it and then you sort of let it go back to normal, it's known as a scattering regime because it can model, for example, two molecules coming in and sort of interacting with each other and then going out. So it's sort of analogous to a scattering problem. And okay, so notice how the smaller epsilon is, the smaller the transition is. And I also plotted, so the asymptotic probability. So I don't know if you can see it here, but this is ever so slightly above this. So, the amplitude hits a maximum and it goes back down, but it doesn't go exactly to 0. It goes to some value, and that's the value we're actually interested in. And so I plotted what that is in terms of epsilon, and you can see that it forms kind of a weird graph. Now, the question is, does this confirm that it is O of epsilon to the n? Now pause here. What would you do if you wanted to check if it's true that the probability is less than or equal to Cn epsilon to the n? Are there any suggestions? what you might do. So I want to check that. So I want to check that this is less than epsilon to the n, and notice that I've got an exponent right here. So how might I rescale things so that I can see more clearly if this is being obeyed?
Logarithm?
Yes, the logarithm, right? And the logarithm, the graph would sort of give you this value of n. So we plotted log and log, and drum roll, please. There you go. That looks pretty. That looks a pretty straight line, say so myself. So yeah, if you plot the log against the log of the asymptotic probability, you indeed get this sort of a straight line graph, which, you know, in a sense, it confirms what was in the literature. And they actually worked this out for a specific, you know, for a specific scattering problem. So they chose a specific value for this theta. I checked that, and I checked another value, another function for theta. So we used, so in traditionally in the problem, what they use is something like 1 over 1 plus t squared. And that is quite nice to work with theoretically, because this has got, if you're familiar with complex analysis, it's got poles, you know, sort of the imaginary values. And I don't want to say too much, but you know, the fact that at around t equals 0, you hit a maximum probability of transitioning is sort of to do with the fact that you are closest to the poles at around t equals 0. However, with numerical simulation, this doesn't decay fast enough. So we use something like, you know, a Koch function, so an exponential decay for theta. And nevertheless, it holds pretty well. So that takes, yep.
Sorry to interrupt you. Can I ask something?
Yep.
You showed us a sphere, like a colorful one, and you said like the chances, I guess like it gets greater, but I realized it's just popped me then after you said it starts to get closer, like it starts to get more narrow in the bottom. So how does it indicate? What how can we interpret? So okay. It has a greater chance in the middle of sphere, but in the bottom it goes narrow again.
Oh, right, okay. I mean, so I don't think there's anything, okay, what I think, so please correct me if I misunderstood your question, but I think you're asking, so, okay, so I know that I can interpret the probability as being a height, and it gets narrow around here, and you're asking what's happening, like what would it mean near the South Pole? Is that sort of what you're asking?
Yes.
Yeah, around here. I mean, so immediately I don't see anything too interesting. So the point is that I chose to start out with the North Pole, but I could have chosen to begin in the bottom energy level. And so the whole situation would be symmetric and you'd be at the South Pole. So the trajectories, of course, never go near the South Pole, because that would mean that there's a probability of 1 that it jumps down, which is that's just not true, because I'm working with small values of epsilon. Does that answer?
Thank you. Yes.
Does that answer your question?
Yeah, thanks.
Okay. Yeah. Yeah, I think, yeah. So that takes me to the end of my talk. So I could just talk about sort of the exciting places where this can be moved forward. So what I've basically tried to convince you is that instead of this traditional approach, you can use the idea of what's known as density matrices. So remember I said how you can, you know, represent being in a state by a matrix. You can use this sort of formalism to derive a set of ordinary differential equations And the theory for ordinary differential equations is very vast and rich. And so, you know, you could maybe take it forward with ideas of, you know, Laplace transforms and whatnot. And I think there's a lot of very interesting opportunities to mathematically treat this problem. And then the question is, so we considered 2 levels. The question is, what about 3 levels? So the effects that you could get at 3 levels is very interesting. So someone in our my maths department actually sort of thought about this problem and sort of considered having 3 energy levels, and sort of, I'm going to butcher the explanation definitely, but try and give you a taste of what the idea is. It turns out, like, if you basically sort of make them oscillate at different times, then there's a possibility that this idea of causality that's very important in physics might be broken. And I don't remember the arguments underlying that, I'm sorry, but you know, it'd be very interesting to check if that's actually what's going on. So, all right. So yeah, so that takes me to the end of my talk now. I'll put my, so yes, I'll also just put my email here, write it down. So it's s.thrasher@warwick.ac.uk, in case, you know, you'd like to sort of correspond and talk about this any further.
Thank you very much for the talk. If anyone has any questions, they can raise their hands through the reactions part. Aren't there any questions, people?
Actually, I have one again.
Yes, please. Yes, sure.
The transitions that we have just seen. So they are non-adiabatic, right?
Okay. Yeah. So so they're due to the non-adiabatic terms, right? So the adiabatic is it's an approximation, and we're interested in the higher order terms, right? That, you know, so yeah, the adiabatic, so the non-adiabatic terms just means that there is an error, you know, there's an error in assuming that it follows the same trajectory.
So, but it is more realistic, right?
Yes, I mean, so it gives you, it's more realistic, and that's almost the entire reason why we're interested in that, because we would really like to know what the probability of transitions are. And, you know, this is a much more complex problem, but sort of under, you know, the Bourne Oppenheimer model has a sort of a similar structure to this, and it's a rather complicated model, and it's potentially possible to try and you know, attack that more intractable problem.
Mm-hmm. And for the value of the epsilon, so the greater the epsilon, the transition probability will be greater, and for the smaller, it will much more likely oscillate on the initial energy level about the electron, right? So is there any like an optimal value of this epsilon so that the problem will give us like the solutions that we have desired so far?
So right, so that's definitely interesting. So okay, so is there a value of epsilon where our theory is most accurate? Is that sort of your question?
Yeah. Or is it matter of interest anyway?
I mean, it's certainly a matter of interest, I would say. So not that I know of, but this value of sort of optimizing though is relevant when we talked about, so, oh, I'm in the wrong one. That's why I can't find it. Remember when I talked about these inequalities? So the idea of optimization definitely comes in there. So you try to
right
at an optimal value. And I guess sort of given an epsilon, there's an optimal value for n. So you do have quite a lot of choice for epsilon. So
okay.
the point though is that we want it to be true for all epsilon. So, you know, yes, sure, you could ask, I guess, is there an optimal value of epsilon? But we're kind of interested in developing this for all epsilon. So given an epsilon, there is an optimal value of n, and you can get an optimal value for the probability. So the n depends on the epsilon, but the dependency is quite complicated.
Okay, all right, thank you.
Yeah. Welcome. More questions?
So in case there is no questions, we can just thank you for coming and giving us a talk. And we are always welcome to, you're always welcome to join and give us a talk about whatever you want.
Thank you very much. Yeah. I hope, I hope everyone could walk away with something at least from this talk. So it was one of my aim.
I'm sure
Thank you very much.
Thank you.
Then I am concluding this meeting. Thanks everyone